Resuming the lecture, there was a bit of disruption because of electricity. Hello, আমার কথা শোনা যাচ্ছে? Hello? Hello? Can you guys hear me right?
Yes, sir, শোনা যাচ্ছে।
So what's going to happen to the current value for the discharging circuit? What we need to understand that current is defined by the Ohm's law, which is I equals to V over R. Now, important for you to understand that in our first circuit, we consider the resistance of the circuit to be R. The second circuit, the resistance of the circuit was 2R. Both of the circuits were, for both the cases, the capacitor was charged by the same initial equal voltage I naught. Sorry, V naught. So initial current for this capacitor is going to be V naught divided by R, whereas the initial current for this circuit, circuit number 2, is going to be V naught divided by 2R. So this is the important part that I need you to understand. But this one shows that initial current for the second circuit will be half the value of the first circuit. So if we try to draw for the same discharging scenario, if we try to draw the discharging circuit for the discharging curve for current I over T, this is going to have a bit different shape compared to the BQ graph, B or Q graph. So let's say this is our I naught. Basically at half, we have I naught by 2 right over here. So our circuit number 1 is going to drain from here and it's going to slowly go nearly exponentially. Circuit number 2 is going to drain from here, is going to go nearly exponentially like that. But what is important, for circuit number 1, the time constant was RC right over here. So I'm going to try to go through the curve piece by piece. So, and for the second circuit, the time constant was 2RC. So this means, although both of them are going to decay exponentially, this is going to take some time to reduce to 37%, but this one is going to take, this one starting from a smaller value, is going to take double the amount of time for the time constant. So this brings us to some interesting curve. I'm going to define two different points. Considering this is our starting value, so I'm going to try to draw the first graph with blue, pretty much similar to what I did over here. Let's say this is our first graph. The 37% of this one is, let's say, about here. So let's say this is the point of 0.37 I naught, and the 37% of I naught by 2 is gonna be, let's say, somewhere over here. So this is 0.37 of I naught over 2. So let's say this is gonna happen within this much time. I might actually consider to draw this horizontal axis parallel with a grid that is gonna give me some benefit. So let's erase that. Better. So let's say this one reduces to 37% within this much time. So let's say this is the 37 per time constant for the first second. So I'm just assuming this number because the scales are not defined, so I can do that. Actually, a bit smaller would be better because I have to accommodate the second graph as well. So maybe up to this much. Let's erase this part. So if this is the time constant for the first circuit, the second circuit's time constant is going to be double of that, which means it's going to be somewhere here, somewhat about over here, somewhere over here. So it's going to start decaying from this point and go through this point and decay over here, whereas I naught is going to go through here and decay through this part. So if I try to draw those curves to my discoverability, I'm making a mistake here. Just a second. I'm messing up something. What am I messing up? constant is going to be double. So anode by anode is going to be double. Standard. Pull that out. What is wrong? Equals to V or R. Equals to V not. Start. We're having the asymptote with the -6 minus 80 y. তোমাদের বই কই দাঁড়াও I'm stuck with this one somehow ভুলে যাই কেন জিনিসগুলো আমি is a certain crossing point for the capacitor discharging. Okay. Seem to have forgotten this part. All right. This is black. And the next one is gonna be there. This is the graph that I was looking for. That there is supposed to be a crossing point somewhere, which I was missing out. So uh, you need to concentrate on this part of the circuit. Have a look over here. So I was trying to get to this one. So এই গ্রাফটা খুঁজতেছিলাম, এই গ্রাফটা খুঁজে পাচ্ছিলাম না। So if we have two capacitor circuits going back from the starting point, we have two capacitor circuits where both the capacitors are identical. They are both charged by the same voltage, source voltage, but one has a discharging resistance of R, the other one has a discharging resistance of 2R. In that case, the one with a smaller resistance is going to have a higher current, initial current, and the one with a bigger resistance is going to have a smaller initial current. However, the discharge rate, the discharge rate is going to be slower for the bigger resistance because it has a resistance is going to allow less current, so the charge is going to leave slowly. Start from a smaller value, but it will go down significantly slower compared to the smaller resistance graph. And this is why this is how the graph shape is going to look like. So all this graph was in V versus V. I actually changed the circuit to I equals to I naught because I wanted to get these two shape variations, and this is the shape that I was looking for. So what I can see over here, the black one is the first resistor, and the second one is the red one is the second resistor. So this one starts from I naught, and it goes down right over here. Now I can actually locate the value of tau equals to RC for different value, let's say 0.2. By 15 minutes. What is the equation for a parallel line? I can't be sure this is a graph. That line over here. Crossing of the 0.37 to represent that these two variables are exactly half. Just a second. Here is okay. 0.37 is 4.44. I'm capable to show you this straight line over here. I was trying to draw a straight line. Okay. I need to label this as B equals to 0.44. Does this help? Slide on it. Y equals to. Anyway, I'm missing up to shape this graph, but what I want you to see, or all of you to see, is that whenever the high resistance graph is going to go through the discharging process, it's going to cut across a certain point because it's discharging at a smaller rate. And if I just have it to give it a little bit of value over here, this is 12. I considered at the initial value of I naught to be 12. That's why the 0.37 of 12 is how much? 0.37 into 12 is about 4.44, which means somewhere around here would be the 37% of this graph. So somewhere over here, whereas the 37% of the second graph, which is half of that, that is 0.22, is gonna be somewhere over here, which is this is 2, this is 1, and somewhere over here is 0.22. So we're gonna have this thing at double the amount of time somewhere over here. So this is the variation of the two graphs that we can have. For the negative axis is not important for us. I want all of you to have a good look for only the first quadrant shape of this graph. So this graph is going to be not in this shape, rather this graph is going to, let me just draw this up roughly. So this is the graph for the I naught to the 1 minus by RC, where is I naught by 2. It's gonna cut through this thing at a point. It will go on like that. This is gonna be I naught by 2 or minus t divided by 2 RC. এই ভ্যারিয়েশন দুটো বোঝা গেছে কিনা, যে গ্রাফটা কেন এরকম হবে। তোমাদেরকে কোনো সব প্লটিং আসবে না, তোমাদেরকে রাফলি স্কেচ করতে বলতে পারে যে draw the sketch of these two graphs approximately. So if you're trying to sketch these two graphs, what is the way you can do easily, whether you have a white piece of space or you have a graph, is that label this thing over here, measure of approximately 0.37 fraction over here, give it mark a dot on this line, and then do the same thing for and take double the amount of time for the I naught value over here, and then just try to draw a smooth curve as best as you can. It's quite unlikely, but it might show you this kind of graph. But these graphs will definitely cross each other. The graph, the circuit with the bigger resistance will have a much smaller discharge rate, and that's why for a significant portion of the discharge process, this one's current is going to get higher than the lower resistance circuit current. Shape variation to বুঝা গেছে কিনা ফলাফল so far.
আরেকবার বলবেন?
আচ্ছা, ফার্স্ট অফ অল এই গ্রাফটা কি বুঝছো?
জি স্যার।
এটা ক্লিয়ারলি বুঝা গেছে যে কেন আমাদের মানে ডাবল রেজিস্ট্যান্সের গ্রাফের কেন টাউটা ডাবল হবে, এটা তো বুঝা গেছে। Tau goes towards so these two graphs are just that. For the case of current, initial current is going to be different for these two circuits. যে সার্কিটের রেজিস্ট্যান্স কম, তার ইনিশিয়াল কারেন্ট যদি I naught হয়, যে সার্কিটের রেজিস্ট্যান্স বেশি, তার কারেন্ট হবে তার half. So if I define this as the starting current, this is going to be half of that. So if I try to plot the discharging current for both of the circuit, let's say we have some ammeters over here and an ammeter over here, and we are recording the current with respect to time by some computer mechanism. So in that case, if we plot those current values with respect to time for both the discharging capacitors on the same axis system, the one that the circuit that has a smaller resistance is going to have a starting discharging current at a higher value compared to the resistance that is double. So if you have a 2 resistance, its starting current is going to be half of that. So what I'm trying to say, if this is 4 ampere, this is going to be 2 ampere. If this is 100 ampere, this is going to be 50 ampere. If this is 1 ampere, this is going to be half ampere. So the starting current is going to be half because you have double the resistance but same voltage. এটা হচ্ছে first understanding point. Is it clear? Why do we have two different starting points? এটা বুঝছো?
জি স্যার।
The next thing is that how we are going to discharge. That this graph is going to discharge with this ratio, e to the power minus t by RC, whereas this one is going to discharge by e to the power minus t by 2RC. So this one's discharging rate is significantly less because the power is half of what we are over here. So I can show you somewhat like this of this form. For example, let's say e to the power minus maybe 2 by 5. That's one type of one value. This one ratio of discharging per second, and then maybe another consider another variable, let's say e to the power minus 2 divided by 10. That's a much weaker ratio because the power is much smaller. If you put it in the calculator, you're gonna see that this one is a much smaller value compared to this one. Both of them are positive values, but because of the power is negative, so it's actually represents 1 by e to the power 2 by 5. This one is 1 by e to the 2 by 10. So the idea is that the second capacitor, which is a larger resistance, is going to discharge significantly slower compared to the first capacitor. So the first capacitor always starts from a much higher initial current. It's going to drop pretty fast, whereas the second capacitor is going to start from half the current, but it's going to drop pretty slowly. So at certain point, the first capacitor's current is going to go down. This crossing point is not highlighted for your syllabus, or there is a very significant discussion about what happens at this crossing point, but we're not going to go through this detail. What I want you to understand that the second capacitor circuit is going to discharge slowly. So this one's decay curve is going to be above the first one's decay curve after a while. And one thing is also very important. If we did draw this to scale within a graph, if let me just draw this. Let's say the I naught 37%. Let's say it's somewhere over here. If this much is the amount of time required for I naught, so this is the amount of time that is tau equals to RC. The 37% required time for the red curve, which is not drawn to scale for my graph. Let's say this fills up over here. So this much, this is gonna be simply tau equals to 2RC. So that's how this is gonna work. So I naught 37% যতটুকু time হবে, I naught by 2 37%, that's it, 3 double time হবে, because these two circuits have different amount of RC. So the first one has a time constant of RC, where the second one has a time constant of 2R into C double. 37% reaction from the starting value হইতে আমাদের সেকেন্ড গ্রাফে বা রেড গ্রাফে ডাবল অ্যামাউন্ট অফ টাইম লাগবে। এটুকু হচ্ছে কি অ্যাসপেক্ট। প্রথমে আমি যখন ফ্রি হ্যান্ড আঁকতেছিলাম আমার এই রেড গ্রাফটা পুরোপুরি এটা নিচে চলে আসছিল অ্যাপ্রক্সিমেট পয়েন্ট দিয়ে, বাট দিস ওয়াজ নট সাপোজ টু বি অল দ্য ওয়ে বিয়ন্ড, ইটস সাপোজ টু ক্রস at this the first graph at some point and then supposed to go above it in the data process, something of this sort. So I was not sure how where to get this point, so that's why I went through the Desmos graph calculator to get my decision. Yes, this is supposed to work like this, and because of the smaller decay rate or smaller discharge rate we are having this crossing. বুঝা গেছে?
Yes, sir.
Anyone else? Any further question, or is this clear to all of us?
Also,
এরপর আমাদের সিলেবাসে যে জিনিসটা আছে ক্যাপাসিটর সিলেবাস, ক্যাপাসিটর চ্যাপ্টার প্লাস ক্যাপাসিটর কম্বিনেশন. Capacitor combination is pretty interesting, but maths can be pretty drastic. I'm gonna help you understand by a certain process that I picked up a couple many years ago. So let's just have a look. Combination, the idea of combination is very simple. Capacitor combination. Well, combinations are basically electrical combination coming of two types, series and parallel. It's pretty simple. So let's try to see two different circuits and see how can we get two different parts of those of the circuit. So let's say if we build up at the beginning, for the sake of simplicity, I'm going to consider the capacitors to be different. All of them are considered to be identical capacitors, so the problem of inductance we're not going to consider that for the time being, but we are going to consider them to be ideal capacitors, but they are different capacitors, which means they have different capacitance value. So if we try to produce a series capacitor combination, let's say this much and this one, let's say we have three of these capacitors connected, C1, C2 and C3. Let's say we are going to connect this to a voltage supply. This is plus, this is minus, this is supply voltage Vs, and we're going to connect it to this voltage supply through a switch. So let's say I'm going to draw a close switch over here, and the capacitor circuit is going to charge up. Now, one thing that all of you need to recall to yourself, first of all, any battery is never actually charged, which means the chemical reaction that happens within a battery that disassociates or separates out positive and negative charges on two sides of it. So one of the electrode becomes positively charged, which is losing electron due to the chemical reaction. The other plate becomes negatively charged due to the chemical reaction. So negatively charged particle plate has an abundance of electrons, whereas the positively charged plate is suffering from the shortage of electrons. So the chemical reaction within a battery is basically responsible, not basically, it's always responsible to make a charge separation. But if you consider at any point of time, what is the total charge of a battery? That will be always zero, because the amount of electron missing in the positive charge plate is almost always, for ideal cases, equal to the amount of electrons available, additional extra electron available on the negative plate. So the total charge in a battery is also zero. And the way a battery works is that if you want to produce a current to a battery, you have to connect both of its ends with a closed circuit. If the negative plate has to give up electrons, the positive plate has to accept equal number of electrons. There is no other way this can happen. You cannot simply take out electrons out of the negative plate of a battery and not feed the positive and an electron. The battery will simply not give you charge. You have to have both the ends connected in a closed circuit so that electrons can leave out of the negative plate and they can enter through the positive plate. This is always going to work that way. The reason I'm trying to remind you of this factor is because what you need to understand, whenever we're going to close the switch, let's say whenever all of these capacitors fully charge up, I mean the charging process is complete. Charging process being complete means the total voltage of this capacitor combination is now equal to the voltage of this whole thing. So if we place, which means there is total capacitance voltage is actually distributed. So let's say this capacitor has a voltage of V1, this capacitor has a voltage of V2, and this capacitor has a voltage of V3, and this is a positive plate, negative plate, positive plate, negative plate, positive plate, negative plate. Now, what you need to understand from Curvature of Second Law, remember, Curvature of Second Law tells us within a closed circuit of closed circuit, the total EMF available is equal to total potential drop, which means that V1 plus V2 plus V3 must be equals to Vs. This is definitely true for every series circuit voltage, Capacitors of second law. However, the individual capacitance being different, the total amount of voltage of these three individual capacitors will be different, but their shared charge would be exactly same. What I'm trying to mean is that, let's say, whenever this charging process happens, let's say through this negative end, Q charge minus Q charge goes out and gets itself settled over here. Once again, capacitor is such a component that never stores charge, it only stores electrical energy. So if this plate has a charge of minus Q, obviously this plate should be charged up by plus Q, which means this plate will now be charged at minus Q and this plate will be charged at plus Q. Similarly, this plate will be charged at minus Q, and this plate will be charged at plus Q. What I needed all of you to understand that through the individually disconnected segment of this circuit, I'm using the term disconnected just to make sense with you. These are not actually disconnected, they're electrostatically connected. So what I need to see that, have a look, if you consider this much segment of a circuit, consider this much segment. So the right plate of the first capacitor and the left plate of the second capacitor. These two circuits are practically not physically electrically connected to the other part of the circuit, which means electrons cannot leave altogether from here. All that they can do is accumulate in one place by producing a shortage in the other place. So whenever we connected the source with this capacitor combination, the very right plate become negatively charged and the very left plate become positively charged because of the source. Within these in-between segments, the charges moved apart by exactly equal amount so that they could produce equal and opposite charge on both sides. Have a look. When this plate is charged at plus Q, this adjacent plate is charged at minus Q. If this is minus Q, this adjacent plate has to be charged at plus Q, and vice versa. It goes on, which basically tells us in the series combination, all the capacitors will have the same amount of charge stored. You cannot have different amount of charge stored through them. Does this idea make sense? In a series combination, all the capacitors Q1 equals to Q2 equals to Q3 equals to, let's say, it's only Q. এই স্টেটমেন্টটা লজিক্যালি বোঝাচ্ছে, এটা বোঝার আরেকটা সহজ উপায় আছে, আমি আরেকটা সহজ উপায় বলছি, সেটাও খেয়াল করো। Let's say we start up the capacitor, close the switch and let the capacitor to flow. This is a series circuit. Through a series circuit, current through every part would be exactly same, and the current should last for exactly same amount of time for all the capacitors. You cannot have different values of current through a series combination, and you cannot have different time for which the current flows through different capacitors. If current flows through capacitor 1, the same current should flow through capacitor 2 and 3 and so on and so forth. Which means the same amount of current flows through this current value will definitely vary. So if I consider that, let's say it is the average current, it's if the same average current flows through the same amount of time through all the capacitors, the amount of charge that will be transferred must be same for all the individual components. There cannot be different components. Do you understand this point?
স্যার
Yes, sir.
Yes.
স্যার ক্যাপাসিটর গুলো কি একটা একটা করে চার্জ হবে নাকি সবগুলা একসাথে হতে থাকতে থাকে?
They're going to be charged over time simultaneously. So it's not like that this one charges up first, this one finish charges, then this one charges up. No, not like that. So what I'm meaning is that if we attach multiple different voltmeters over here, let's say this is voltmeter 1, this is another voltmeter, and let's say this is another voltmeter. If we connect multiple voltmeters across these capacitors individually to see their voltage development, what we'll see that the moment we close the switch, all of these 3 voltmeters are gonna start to build up voltage values, but they're not gonna be by equal amount. If this source has a total voltage supply of, let's say, 20 volt, once the capacitor stops charging, it means once the charging process is complete, then the sum of this voltmeter, and this voltmeter would add up to 20 volt, but they will all go from 0 to their maximum value simultaneously. Did I get your question answered?
Yes, sir.
Beautiful. Everyone else, এই পার্টটা বুঝা গেছে? I hope so. আচ্ছা, এই দুটো জিনিসকে ইউজ করে আমরা ক্যাপাসিটরের কম্বিনেশনের বেসিক ফরম্যাট ডিভাইড বের করতে পারি। একটা জিনিস আমরা খেয়াল করি সেটা হচ্ছে ক্যাপাসিটরের জন্য আমাদের কোর ফর্মুলা ছিল Q = CV। এখানে আমাদের V এর একটা ইকুয়েশন পাইছি আমরা, সো এখানে যদি আমরা V কে সাবস্টিটিউট করি, V এর ফর্মুলা আসবে V = Q/C। সো আমরা এই এক্সপ্রেশনটা এখানে সবার জন্য বসাই। So Q যেহেতু সবার জন্য সেম, so I'm going to use the same Q divided by C1 plus Q divided by C2 plus Q divided by C3, which should be equals to the total amount of charge that leaves out of the battery, Q divided by, let's say, total capacitance of the circuit. So source এর জায়গাতে আমরা combined series combination এর combined capacitor বললাম। So এখন যদি Q সবখান থেকে কাটা দিয়ে দিই, what you're going to get 1 by C1 plus 1 by C2 plus 1 by C3 equals to the equivalent capacitance of the series combination, which is pretty interesting because you can see that the series combination formula for capacitance combination is just similar to the parallel combination of resistors. So it's the other way around. Resistance এর জন্য আমাদের series combination এর formula কেমন ছিল? শুধু add করলে হয়ে যেত, right? R1 plus R2 plus R3 equals to RS. But for the parallel combination for resistance was for the inverse format. Whereas for capacitor, in the series combination of capacitance is the other way around. So it's what works that way. I'm going to go for the second type of combination that we can have, which is the parallel combination. We're going to see that the parallel combination is going to give us the shape similar of series resistance combination formula. So let's consider a parallel combination for a capacitor. Let's say we have three capacitors, ideal capacitor, but different capacitance. Let's say these are common point. They are all connected to a battery through a switch. And let's say the source of this voltage is Vs. Now, what we should see over here that because they are all connected in parallel, let's say this is capacitor 1, this is capacitor 2, this is capacitor 3. You need to understand that these three capacitors, they are all individually connected to the supply because current can directly flow through this way and back. Current can flow out of the battery through this way without any effect of the other branches and back, and same for the third branch as well. So because the capacitors are all connected individually to the supply, all of these capacitors individual voltage should be exactly same, which also brings us to the idea of the Curvature of Second Law, which means if we consider three different loops over here, let's say the circuit loop is pretty much the same. So let's say this is a circuit loop. Then you can consider one loop to the top branch. So you can consider this one as a closed loop. If you consider this much as a closed loop, you're gonna get Vs equals to V1. Let's say this is the voltage of this V1, this is V2, and let's say this one's voltage is V3. And then if you consider for the second loop, second path, consider this one exclusively, then you also get a closed loop like this, which also gives you Vs equals to V2. Likewise, if you consider the third path, this also happens the same way. So this is V3 and this goes on up here and it becomes back down over here. So Vs equals to V3. So basically what I'm trying to mean, for a parallel combination, all the capacitors voltage would be exactly equal to each other and which will be equal to the source voltage as well. So this is Vs equals to V1 equals to V3, V2 equals to V3. So voltage সবার জন্য same হবে. How about current? Will the current be equal for all of them? The answer is obviously no, because the key current that comes out of the battery, let's say that is I, that gets divided into three different parts. There is no reason that these three currents should be equal because they have different capacitance. So this is our I1, this is our I2, and this is our I3. And what Capacitors first law tells us, if we apply it for this branch, that this input current should be equal to I1 plus I2 plus I3. Do you understand this part? Capacitors second law, first law. Now, if we multiply this thing for the same amount of time for which that current flow happens for all of them, we can write the capacitor that comes out of the source. We should write source because S might actually be in series, must be equal to the charge stored in capacitor 1 plus charge stored in capacitor 2 plus charge stored in capacitor 3. So in this case, because the parallel combination, the total charge that is going to be coming out of the source. For example, let's say if from here we are having Q charge coming out, if this one stores Q1, this one stores Q2, this one stores Q3, the sum of their charges will be all fed from the supply. So for the parallel combination, the sum of the charges is equal to the charge coming out of the supply. Does this idea make sense so far? তোমাদের ডেরিভেশন পরীক্ষায় আসবে না, তোমাদের অ্যাকচুয়ালি
Yes,
ফর্মুলা
sir.
থেকে ম্যাথস করা লাগবে, বাট আনলেস ইউ আন্ডারস্ট্যান্ড হাউ দ্য থিং ওয়ার্কস, ইন্ডিভিজুয়াল ক্যাপাসিটর সার্কিট হ্যান্ডেল করার সময় তোমার ঝামেলা করবে, কারণ তোমাদেরকে কম্পোজিট কম্বিনেশন দিয়ে তোমাদের কাজ করতে হবে। সো সেই কেসে কিছু বুঝার প্রবলেম হয়ে দেখা যাবে। সো এখানে যদি আমি সিম্পলি ভ্যালুগুলোকে রিপ্লেস করি, লেটস সে দিস ইজ দ্য টোটাল চার্জ কামিং আউট অফ দ্য সাপ্লাই, সো আই ক্যান রাইট the combined capacitance of the combination is CP multiplied by the supply voltage. So if you consider this whole thing has a capacitance of CP, capacitance of the parallel combination multiplied by the supply voltage, this should be equals to capacitance of 1 into supply voltage plus capacitance of 2 into supply voltage plus capacitance of 3 into supply voltage. We can cross out all the supply voltages from all sides because they are in multiplication forms, that we get parallel combination. That equivalent capacitance for a parallel combination is given by the addition of the capacitance of all the individual capacitors in branches. So this is the interesting formula that we have. So the formulas by shape are exactly opposite to what we have learned for the series combination. So for the resistors, the series combinations are addition and the parallels were inversed. But for the capacitance, the series combinations are inversed and the parallel combinations are addition. And remember it by that manner, that is just opposite to resistor formula, and that would save you a lot of trouble. And then the idea of the distribution of charges is actually also very important. What essentially comes up on the next part of the discussion is how we're going to deal for combination of capacitors. For example, if we have some capacitors which are a combination of multiple capacitors, how we're going to do that. For the sake of simplicity, for your syllabus, whenever we are going to deal with combination of capacitors, in all of the question papers that I have seen, I mean, there might be some exception that I haven't looked, I have overlooked. But for most of the part of the questions that I've seen, whenever we are going to deal with combination of capacitors, they have always gone with identical capacitance for the sake of easier calculation. So I'm going to show you some example of identical capacitors in mixed combination. I mean, there will be a series parallel combined up, and also how much voltage can we safely apply to that, and what does that mean? I mean, safely apply safely applicable voltage of a capacitor. What does that actually mean? I'm going to explain that as well. I'll try to show you at least one example for dissimilar capacitors. How could that work? Which is pretty much the actual scenario for what actually how circuit boards are actually designed. So that is somewhat something that you might want to know if you're really trying to look forward to understand how the capacitor circuit actually works in real life. But that is not very significantly highlighted in the syllabus. Then again, if the teachers feel like that we're going to set up a question of dissimilar capacitance in this year's math, if they do that in our actual question, there is nothing you can say about it. So hands down, you have to know about it. You should know about it, but if you don't know about it, for most part, you are safe. So yeah, I'm going to try to show you some example of that as well. So let's have a look. If we have a combination of identical capacitors, so identical capacitors means, so if we consider the capacitance for identical capacitors, let's say we consider C capacitor. So we're going to build up combinations using identical capacitors, which we have access to many of those. Let's say all of those have capacitance C. This capacitance value could be anything, some farad, microfarad, picofarad, whatever. But we're going to consider identical capacitors. So let's consider one combination. So let's say combination that looks like this. Okay. We have just seen these circles, you know, from circuit symbol. These are the circles. These circles represent the connection point of a certain circuit, or these are points where we can actually connect multiple components, maybe source, maybe a voltmeter, whatever. Can you please try and tell me, by doing calculation, what would be the equivalent capacitance of this combination? But all of the capacitors have a capacitance C. What will be the equivalent capacitance of this combination? Remember, for series combination, you have to go for the reverse formula. For parallel combination, you have to go for the addition formula. I'm going to do this for all of you to give you a bit of a sense for how this can be achieved easily. For the next upcoming parts, I'm going to ask you to do this for and try and tell me the answer. So the easier way to do this thing is that you go for the most inner part of the circuit or the most difficult part. So you can see that particularly this is a series circuit. There is one capacitor and there is a whole combination of parallel branches. Within these parallel branches, there is one branch which has another series combination. So I'm going to start with this one. The combined capacitance of these two things, which are connected in series, is going to be C by 2. Do you understand why?
Yes, sir.
1 by C plus 1 by C equals to 1 by CS. So CS is going to be C by 2. Then we are going to try to add up the value of C by 2 and C. So if we add all these up, the combined capacitance for the parallel combination is going to be C plus C by 2 plus C, which is going to be 2.5 C. And then we have to apply parallel formula for these two as well. So now I actually have to do some calculation. So now the final series combination is going to have a capacitance of 1 upon C plus 1 upon 2.5 C. So actually I have wrote it wrong. This should be 1 by CS. So 1 by CS equals to C is the LCM. So 2.5 plus 1 is 3.5, which is CS should be equals to C divided by 3.5. Is my LCM okay? Not quite. Help me.
Sir, second. Yes, sir.
Series combination total capacitance হচ্ছে 5/7 5/7 করলে কত হয় 0.7143 0.7143 C. This is the total capacitance of this whole combination. সেটা হচ্ছে capacitance calculate করার basic mechanism. The combined capacitance calculate. If we have equal capacitance, that is actually quite simple. We can go part by part. However, if we had dissimilar capacitance, obviously the values are going to be given to us. In that case, you just have to do some long mathematical processes. Try to use the best of your calculator and do not forget. Actually, I think I forgot. Did I forget? No, I didn't forget. I actually wrote it the other way around. Do not forget to do the reversal of this form of this expression. So if you're working with numerical values, it's always best for the series combination to go CS equals to C1 inverse 1 plus C2 inverse 1 plus C3 inverse 1 plus the whole inverse 1. The typical shape that I usually try to get in the student's head for the ease of calculation and not to mess up the values. That's one thing. Okay. Now let's consider a different scenario. Let's say we have a capacitor circuit that looks like, so I'm going to go for a very simple capacitor circuit. Let's say we have a very simple capacitor circuit that looks like this. Okay. Let's say we have a capacitor combination that looks like this. The question tells us each of these capacitors are labeled 30 microfarad 6-volt max. Capacitors are usually labeled by these two variables. What this means, sometimes they do not mention the max, they only write the 6 volts. It actually means that it is the maximum voltage. It actually means that what is the maximum voltage that you can apply to this capacitor so that it wouldn't fail. You might wonder, what does it mean for a capacitor to be failed? Let me just explain this part and then I'm going to get back to this calculation. Have a look. Whenever a capacitor is charged, say we have two plates over here of a capacitor. Here are the two connecting wires, and within this plate, let's say we have a piece of dielectric medium, which is the insulator medium, that is responsible for the atomic level deformation of the electron shells and the electron, the negative charge center and the positive charge center, which is the nucleus. So whenever they are not perfectly uh, overlap onto each other's position, we have a bit of distortion, and that distortion is by which capacitor stores energy. However, one thing that you need to understand: if we start to apply voltage across this capacitor, let's say we're going to apply some voltage. Let's say we're going to increase the value of the voltage. To start to increase the voltage, so we are going to charge this positive plate high positive voltage, and this is going to be high negative voltage, so on and so forth. You should remember one thing: there is no such thing as perfect insulator. Given enough voltage, anything and everything can be made to conduct electricity. I say it again: there is no such thing as a perfect insulator. Given enough voltage, anything and everything can be made to conduct electricity. The most beautiful common example is lightning. Atmosphere is a gaseous medium, disconnected particles, but lightning can happen from clouds to ground through atmosphere. Atmosphere is not supposed to conduct electricity, but when there is enough voltage buildup by the process of cloud formation and so as such, the voltage difference can make the atmosphere to conduct electricity for a small duration of time by producing a very high value of current to discharge its voltage difference. So what it means is that if we start to increase the voltage across the two plates of the capacitor, there will come a certain point at which electrons are going to actually jump or spark through this material, no matter how good of an insulator material this is, no matter how, even if this is vacuum, doesn't matter. There is definitely a certain voltage value for whatever medium you choose, or even if you choose no medium at all, the electrons are going to start to discharge to this medium, and electricity is going to start to go through the bulk plate. This is the point where the capacitor no longer can be charged to a higher voltage. This is the point, this is the limiting voltage of the capacitor to which it can maximum. And if this thing actually happens, that electrons start to flow, you have to understand that whenever lightning happens, a very high voltage produces a very high current over a very small amount of time, and the heat generated by the electric current is given by P equals to I square R. This is the electric power form of equation. So the energy or heat energy converted can be given by I square RT. This T for a single spark is actually pretty small, but the I value for a single spark can be pretty large. Because there is a square over here, the amount of heat generated, if there is a short circuit between the two places of the capacitor to the capacitor, the energy generated can be very high, which will almost immediately burn up the insulator material that is in between, and the capacitor will practically lose its purpose. This is when a capacitor becomes unusable, and we have to discard it, replace it. Do you understand the physical phenomenon that I just tried to explain?
Yes, sir.
এটা এই জন্য বললাম যে what do we mean by maximum voltage? What we mean is that there is a certain maximum voltage for which the capacitor was designed. For example, capacitors which we use in the ceiling fan for our house, they are AC capacitors. They are pretty large. They can handle a pretty high voltage, 220 volt AC. But the capacitors that those are used on the motherboard for a computer, they are extremely small. They are like very small capacitors which are plugged in. Depending upon how much voltage are you going to handle and how much current do you need to pass through it, you can change the capacitor's shape, size, material choices, so on and so forth. It all comes to key consideration: how much voltage you have to deal, how much current you have to deal, and how much physical space do you have in the electrical circuit design to accommodate that component. Because space is a very important factor. You cannot simply make a computer motherboard that is as big as a building with using large capacitors and whatnot. Maybe it will work, but you cannot sell it because it's inconvenient, and in the competitive market, it's not useful or it's not good. It's going to cost a lot. So physical space requirement is also a very important factor. Anyway, that's somewhat not very much important for ourselves. What I'm trying to get at is I was trying to explain what does this factor actually mean. This is volt max. This means that this is the maximum voltage that we can allow safely across a capacitor. Anything higher, the circuit will not work, capacitor will blow. Now, let's say we have a capacitor combination that is built up with identical capacitors, each of which are labeled by this value. The question usually asks you to first calculate what is the combined capacitance of this capacitor. You can calculate that. And then they will ask you what is the maximum voltage that can be applied across the two combination connection point, let's say AB. What is the maximum voltage supply that can be connected over here? Here's the deal. You need to understand this capacitor, each capacitor can handle a maximum of 6 voltage. If you want this whole thing to work, the maximum voltage across the maximum voltage capacitor should not be more than 6 volts, or should be at best maximum 6 volts. You can have lower than that, that's okay, but you cannot have higher than that. What do I mean by this? Try to understand. One easy way that I always try to teach the students whenever they are trying to go for combinations like this, have a look over here. Please try to understand this part a bit carefully. This is the capacitor combination. If I consider this much part of the capacitor, this is a disconnected part of the capacitor, right? This part is not connected to the left side, this part is not electrically connected to the right side, which means the total amount of charge over here should be equal and opposite on both sides. So let's assume if this plate has a charge of minus Q, these two plates together should have a charge of plus Q. Now, because they are identical capacitors, interesting factor, because they are identical capacitors, obviously the amount of charge on these two plates is simply gonna be half. Do you agree on this one?
Yes, sir.
Because equal amount of charge has to be separated by on opposite sides. This also brings to the idea that obviously then this would mean that this one will be minus Q by 2, and this one will be also minus Q by 2, and this one will be actually plus Q. I didn't have to write all of these parts, but I'm writing this thing to make sense with you. What I'm trying to mean is that this capacitor can store a maximum of Q charge when these two individually will store maximum of Q charge. Now, because Q equals to CV, try to remember, try to understand. C in this case is same for all of them. So C is a constant. I mean, for this scenario, C is I shouldn't say constant. I should say C is the same for all the capacitors. So Q and V would be proportional. We don't need that, but what I'm trying to mean, if for Q charge you have a voltage of V, then for Q by 2 charge, you would have a voltage of V by 2. Which brings me to the idea that if this capacitor by its own has a voltage of V across it, individually, this combination, I mean across this capacitor or across this capacitor, practically what I'm saying that across this parallel combination, the voltage across this parallel combination is gonna be V by 2. এই পার্টটা বুঝা যাচ্ছে কিনা? Because of the charge sharing, this one is having V voltage, this one is having V by 2. Now try to have a compare between these two values. V is bigger than V by 2. We have said that maximum 6 volt maximum apply করা যাবে. So definitely maximum voltage should be applied here. So if we apply 6 volt over here, what should be the value applied over here? Logically, V by 2 gives you how much? 3 volt. So total, how much total voltage can be applied across AB? 6 volt plus series combination, 3 volt, 9 volt, which means if we apply a maximum of 9 volt supply across this combination, the first capacitor, single capacitor, solo capacitor, is going to take 6 volt out of it. The parallel combination is going to take 3 volt out of it. They are not experiencing maximum voltage, but this one is experiencing maximum voltage. If we increase the value of this voltage, we're going to have some trouble, because in that case, this one is going to have a shared voltage of bigger than 6 volt, which is going to surpass our limit. We don't want that. এই ক্যালকুলেশনের প্রসিডিউরটা বুঝা গেছে কিনা বলবান? I started by considering charge, then I slowly worked my way to voltage, and then I added the whole thing together to get a total value.
Sir.
I'm going to show another example, although we are pretty much close to our end point time, but I'm going to show another example just to make another clarification with you. What if I give you a bit more complicated circuit? Let's say if I want to give you a circuit that looks like this. We have two capacitors in parallel. With that, we have three capacitors in parallel. And in this case also, they are all identical capacitors, and the question say that they have 6-volt max applicable for individual capacitor. Now, how much voltage? What is the maximum voltage that you can apply across this AB connection point? The idea is still very much same. What you need to understand, I'm going to once again draw up this line. Have a look. This punch part is the disconnected part, or the segregated part, or the not directly electrically connected part of the circuit. So this is the different part. You might wonder, what if there are multiple of these? I'm going to show you, no big deal. In this case, this is the individual part of the circuit, which means on the left and on the right, we're going to have the same amount of charge. So try to understand this thing. You want to be smart to choose the amount of value so that you do not fall into trouble. So let's say if you consider these two together to store Q charge, let's say these two stores Q charge and this 3 stores Q charge. So the charge within this capacitor, if considered Q by 2, the charge stored on this capacitor should be also stored Q by 2. So I'm considering these two plates to be storing Q by 2 charge. I'm not considering the other plate. I'm considering only the one plate of the capacitor. Let's say, just for the sake of simplicity, let's say this is minus Q by 2 and this is minus Q by 2, which tells us the total amount of charge by these two plates is minus Q. That should be divided onto these 3 plates by equal amount, because they are all identical capacitors. So this should be plus Q by 3, plus Q by 3, and plus Q by 3. Do you understand what happened here? I did not consider this one to be Q. I could do this. I could consider this to be Q, this to be Q. In that case, this should be written as 2Q by 3, which is also okay. You're gonna get the same result. But I wanted it to be written like that. I mean 2Q by 3 দিয়ে করে দেখাইতে পারবো, সমস্যা নাই। বাট এই কনসিডারেশনটা বুঝছো কিনা, যে লেফট সাইডে যতটুকু চার্জ থাকবে কম্বাইন্ডলি, রাইট সাইডে ততটুকুই পজিটিভ চার্জ, অপোজিট চার্জ থাকবে কম্বাইন্ডলি। সো ওই জন্য আমি এটাকে হাফ ধরলাম, এটাকে 1/3 করে ধরলাম। Now the remaining part is pretty simple. So this actually means, because all of them have that same voltage, so I'm going to write Q equals to CV. So Q by 2 charge should have a voltage of V by 2, Q by 3 charge should have a voltage of V by 3, which means the total voltage across this parallel combination is going to be V by 2, and total voltage across this parallel combination is going to be V by 3. And এই দুটো রেশিওর মধ্যে বড় কোনটা? Which one is bigger between these two fractions? What do you think?
V by 2.
V by 2 or V by 3?
V by 2.
V by 2 is the bigger fraction. V by 2 is the bigger fraction. So maximum voltage should be applied to the bigger segment. So this much should be 6 volt. Now try to think about it. If V by 2 has to be 6 volt, then V should be how much? V becomes 12 volt, right? I'm actually writing on the left side, I mean opposite way, because I was starting to do it that way. So in this case, the considered V, which is not the voltage across any of those, this segment should have V by 2, this segment should have V by 3, but the considered value V for Q charge should be 12 volt. So V by 3 should be 12 by 3, which is 4 volt, which means ultimately we can say this part of the circuit can experience a maximum of 6 volt, in which case this part of the circuit should have a maximum experience voltage of 4 volt. Together we can apply a maximum of 10 volt across this combination, so that the capacitors do not burn out. Does it make sense? One last combination, then we will call it a day.
Sir, 12 volt তাহলে কি ইন্ডিভিজুয়াল মানে 12 ভোল্ট কি হচ্ছে ভ্যালুটা?
এই 12 volt কি জিনিস?
হ্যাঁ,
This 12 volt is actually the voltage that would be responsible for V amount of voltage. So if any capacitor had Q charge stored in it, it would have 12 volt voltage across it for that capacitance value. But as for my considered calculation, none of these capacitance had Q charge stored in it. Two of them had Q by 2 each, and 3 of them had Q by 3 each. So if any capacitor had Q charge stored within them, they would have a total voltage of 12 volt across them.
Okay, sir, got it. Thank you.
বুঝছো?
হ্যাঁ স্যার বুঝছি।
আচ্ছা, এটা হচ্ছে একটা জিনিস। আমি আরেকটা সার্কিট একটু করে দেখাই। মনে করো আমি যদি এই সার্কিটটাকে কিউ দিয়ে করতে যাইতাম, মনে করো I'm gonna draw the same exact circuit, let's say considering the exact same circuit. Actually I shouldn't say circuit, but it's a combination. I'm using these two words replaceably, which shouldn't be a very good practice, my bad, but I hope it makes sense. As long as it makes sense, I'm happy, but it's not correct. So let's say we have this combination. Once again we have the same thing, 6 volt max. So what is the maximum voltage that we can apply across two sides, AB point? If I consider these capacitors to have Q charge stored in each of them, then together the left side has 2 Q charge, Q over here, Q over here. So these three together altogether should also store 2 Q charge, which means one of them should store 2Q by 3. This one should also store 2Q by 3. This one should also store 2Q by 3. One of the plate of the capacitor should have this much charge stored. Now try to have a look. The idea is that Q equals to CV. C is same for all of them, which means if for Q charge store we have a voltage of V, then for 2Q by 3 charge stored we're gonna have 2V by 3 volts. So this part of the circuit should have V voltage across it. This part of the circuit should have 2V by 3 voltage across it, volts across it. These are maximum voltage because this is obviously smaller. This is a proper fraction. So this one should be 6 volt. This one should be 2/3 into 6 volt gives you how much? 4 volt. Total you're gonna have 10 volt. Same thing. If the calculations are correct, you're gonna end up with the same result. I could have also started from here. I would go cube, cube, cube. In this case, this would be 3Q by 2, 3Q by 2. Ultimately, the whole thing would be exactly same. বুঝতে পারছি বলবান? এই ক্যালকুলেশনটা কি বুঝছো? সেম জিনিসই ডিফারেন্ট ভাবে করছি, বাট এন্ড রেজাল্ট ইজ সেম. One very last thing, because I really want to this last circuit to be included within this video lecture. If we have multiple stuffs, same question, 6 volt max. Now how can we do this thing? What's going to happen over here? They're all identical capacitors, no problem there. To do this, we have to distribute the voltage first. What do I mean? Have a look over here. For this whole capacitor combination, if you even because Q equals to CV, and this is just a capacitor combination. If this capacitor has Q charge stored in it, I'm starting from this one, and has V voltage, this to have half of it. Apparently it looks like it should be half of it, but should it be half of it? The answer is no, because within here we have something else. So it would be a better idea not to start with the outside part, rather to start from the most inside part. So I'm gonna try and do that. Have a look. Let's consider these capacitors are gonna have Q charge stored each, because they're in parallel, they have to have the same voltage and same capacitor. Now, if this two has Q charge, this one should have 2Q charge, because these two pairs QQ, this pair should be 2Q. If this one has 2Q charge, because Q goes to CV, the voltage of this one should be 2V. So logic tells me what? Have a look. the voltage for this branch, I mean the voltage across these two plates should be in terms of V how much? A parallel combination voltage কতটুকু? V
3 volts.
এটার একার ভোল্টেজ কত? 2V। তাহলে এই দুটো কম্বাইন্ড ভোল্টেজ কত হবে? সিরিজ কম্বিনেশন ভোল্টেজ কত হবে?
3 volts.
3V.
It should be in terms of V, it should be 3V. Beautiful. Which shows us this one should now have a voltage of 3V across it as well. Comes to the point that this one should have a total charge of 3Q stored within it. So I consider the voltage equalization. Other than that, you could also go it in this manner that this branch has 3Q charge, this branch has 3Q charge, so this branch should also have 3Q charge, so it could also go that way. Now, have a look over here. This plate has a charge stored of 2Q. This plate has a charge stored of 3Q. This is the disconnected part of the circuit, which basically tells me that this plate should have a charge stored of 5Q, giving me a voltage value of 5Q. So let's go part by part. I'm gonna circle them by blue. This circuit should have, this capacitor should have a voltage of 5V across it. This one has 2V, this one has 3V, this two has V each. Which one is the biggest of all of those? 5V is the biggest. So maximum volt 5V should be equals to 6 volt max, 6 volt. That gives us the value of V should be 6 by 5, which is 1.2 volt. So V এর যে ভ্যারিয়েবলটাকে ইউজ করে আমরা এক্সপ্রেশনটা গুলো বানাইলাম সেটা ভ্যালু হবে 1.2 ভোল্ট। তার মানে হচ্ছে এটার ভোল্টেজ হবে 1.2 ভোল্ট, এটার ভোল্টেজ হবে 2.4 ভোল্ট, আর এটার ভোল্টেজ হবে 3.6 ভোল্ট। দেখো বুঝা যাচ্ছে কিনা? V in this case is not the the voltage of this very inside capacitors, which we considered first, and we slowly worked our way out from the most innermost part, because that's the easier way. That way you have to handle with less amount of fraction. I could have started from here and slowly go inside. In that case, we're going to have to deal with a lot of fractions. I personally don't recommend this, and just not to mess up with your brain, I'm not going to show that. But if you are interested, you can try it on your own. So
3Q টা কিভাবে পেলেন?
3Q টা পাইছে হচ্ছে দেখো এই উপরের ব্রাঞ্চের একপাশে টোটাল ভোল্টেজ কত ছিল? 3V। তাহলে নিচের ব্রাঞ্চেও প্যারালাল ব্রাঞ্চে ভোল্টেজ 3V থাকবে না? প্যারালাল ব্রাঞ্চে তাহলে এখন Q তো Q ইকুয়াল টু CV, তাহলে V আর Q প্রপোর্শনাল। সো 3V এর জন্য রিলেভেন্ট চার্জ কত হওয়ার কথা? 3Q।
বুঝতে পারছি।
আরেকটা উপায় হচ্ছে তুমি যদি এই সার্কিটে টোটাল স্টোর চার্জ দেখো, এই ক্যাপাসিটরের মধ্যে চার্জ স্টোর হচ্ছে কত? ফর এক্সাম্পল, if you consider the charge stored on this capacitor is Q and charge stored on one pathway is also Q. So I'm actually in a pseudo way, or in a more hidden way, I'm actually going for Kirchhoff's second law. So I'm going for one branch. That usually can prove to be somewhat difficult, but considering the voltage and working it way backwards actually easier. So try to adopt that I consider that I found out the total voltage across this branch and I applied that same mechanism over here for it to be 3 volt. বুঝছো? এখানে আমার যদি আরেকটা ক্যাপাসিটর থাকতো তাহলে আমি 3 ভোল্টটাকে দুটো ভাগ করে দিতাম, তখন আমার 1.5 ভোল্ট ইচ হতো, তখন 1.5 কিউ আসতো। মেক সেন্স?
জি স্যার।
সো এখান থেকে এটা পেলাম, তাহলে 5 ভোল্টে 5V এর ভ্যালু হচ্ছে 6 ভোল্ট, এদিকে 3 ভোল্টের ভ্যালু হচ্ছে 3.6 ভোল্ট। সো তার মানে এটা ভ্যালু হচ্ছে 3.6 ভোল্ট। তার মানে ম্যাক্সিমাম অ্যাপ্লাই করতে পারবো কত এখানে? 5 প্লাস 3.6 ইকুয়ালস টু 8.6 ভোল্ট। সো এই সার্কিটের অ্যাক্রসে ম্যাক্সিমাম 8.6 ভোল্ট অ্যাপ্লাই করা যাবে, এর বেশি অ্যাপ্লাই করা যাবে না।
6 plus 3.6 হবে না?
Oh, sorry. Yeah. I'm really sorry. Thank you. 6 plus 3.6 হবে। 5V এর ভ্যালু তো হচ্ছে 6 ভোল্ট, এদিকে 3 ভোল্ট, 3V এর ভ্যালু হচ্ছে 3.6 ভোল্ট। হ্যাঁ, মানে 5v plus 3v which is 8v, 8v should be 9 as well. Thank you. এই কম্বিনেশনের ক্যালকুলেশনের আইডিয়াটুকু বুঝা গেছে কিনা? আমরা ওয়ার্কশিট থেকে আরো কিছু ম্যাথস করবো, করলে জিনিসটা আরো একটু ক্লিয়ার হবে। ফর দ্য টাইমিং ফান্ডামেন্টাল টুকু ক্লিয়ার হলে ওকে। তোমাদের সাথে আমার কালকে ক্লাস আছে, কালকে ইনশাআল্লাহ আমি অবশ্যই ক্লাস নিব এন্ড উইল পিক ইট আপ ফ্রম হিয়ার। তোমাদের সাথে আমি কালকে অবশ্যই কিভাবে ক্লাস নিব। তোমাদের কালকে ক্লাস হচ্ছে 1:30টায়, রাইট?
Yes, sir.
I'll be on inshallah. Assalamu alaikum.